In this video, I'd like to talk about the quantum mechanical model of the hydrogen atom. But let's begin with some review. What does it mean to say that the energy levels in the hydrogen atom are quantized? It means the energy levels are fixed at specific values and they do not change. And the hydrogen atom can only exist at these specified predetermined energy levels. How do we know they're quantized? Because hydrogen atoms, when they're in excited states, give off a line emission spectrum rather than a continuous spectrum. What does each line in the spectrum correspond to? Each line in the spectrum corresponds to a specific transition in the hydrogen atom from a higher quantized energy level to a lower quantized energy level. The wavelength of the line corresponds to the energy being given off in that transition. We finished our last video with the Bohr model of the hydrogen atom. We talked about what aspect of it works, namely that it quantitatively predicted the wavelengths of light seen in the hydrogen emission spectrum, and we talked about what doesn't work, namely the physical interpretation of the electron moving in a circular orbit. So let's move on now to the quantum mechanical model of the atom. Well, first question is, if Bohr is wrong, what is the electron in the hydrogen atom doing? Let me talk about the advances made by some scientists in the early part of the 20th century. A French physicist named de Broglie said, well, we know about the dual nature of electromagnetic radiation. If light can be both wave-like and particle-like, maybe an electron can be wave-like and particle-like too. And in fact, subsequent experiments showed that electrons do behave like waves. If I fire a beam of electrons at you, that beam of electrons, even though it's made up of particles, has wavelength and frequency. Heisenberg, in the famous Heisenberg uncertainty principle, said we can never know the exact position and speed of a particle at the same time. So we should stop trying to think about the electron, particularly in the hydrogen atom, as having a particular location or pathway. Schrödinger said, well, I'm going to consider the electron in the hydrogen atom as a wave rather than a particle. And he derived wave functions. Wave functions are mathematical functions that give the amplitude of the electron wave in terms of the three Cartesian coordinates. The wave functions never tell us exactly where the electron is. It simply gives the probability of finding an electron at a given place, namely where the electron is most likely to be. These wave functions are given a name that's probably one of the worst choices of words in all of science. They are called orbitals. Why is that a bad choice? What does orbital sound like? It sounds like orbit, but they're not orbits. So get the idea of Bohr's circular orbits out of your mind. An orbital is a region of space around the nucleus where the electron is likely to be found. It also corresponds to a particular energy level. And the hydrogen atom has many different orbitals of different sizes, shapes, and energies, and that's what we're going to talk about in this video. So, a good place to start would be at the ground state, that is, the lowest energy state. When the hydrogen atom is in its ground state, the electron is likely to be found in a spherical region around the nucleus. This diagram represents a hydrogen atom. The black plus sign in the center represents the nucleus. The blue dots represent the probability of finding the electron at that particular place. The density of blue dots indicates the greater probability. So as you can see, because the blue dots are densest closest to the nucleus, that means that the probability of finding the electron is greatest near the nucleus. As you move away from the nucleus in a spherical fashion, you can see that the density of the blue dots decreases. So that means that the probability of finding the electron decreases as you move further away from the nucleus. We call this orbital the 1s orbital. As you'll see, orbitals have designations. This is called the 1s. This corresponds to the ground state. In the excited state, there are lots more orbitals. So let me now give you a very concise summary of the quantum mechanical model of the atom. In the quantum mechanical model, the atom has what are called principal energy levels, which you may also have heard of before, called shells. They are indicated by the letter N. This should look familiar. N equals 1 is the ground state, the lowest principal energy level. N equals 2 is the first excited state. N equals 3 is the second excited state, and so forth. The important thing about these principal energy levels is that they correspond energetically exactly to Bohr's quantized energy levels. The energies of the principal energy levels in the quantum mechanical model are the same as the energies that Bohr predicted. The only difference is they're not circular orbits. An additional difference in the quantum mechanical model of the atom is that each principal energy level is divided into one or more sublevels, which are also called subshells. They are designated by a number and a letter, for example, the 1s sublevel or the 3p sublevel. The number is the principal energy level it's in, that is, the value of n. The letter tells you what kind of orbitals are in the sublevel. Finally, each sublevel contains one or more orbitals, and again, an orbital is a region of space around the nucleus where the electron is likely to be found. On the next slide, I'm going to show you a potential energy diagram that shows the first 4 principal energy levels in the hydrogen atom. Energy is increasing from bottom to top, and I have the 4 principal energy levels, n equals 1 through n equals 4, labeled. Let's start at the bottom. In n equals 1, the first principal energy level, there is a single sublevel called the 1s sublevel, and it contains a single orbital indicated by the horizontal line above the 1s. In the second principal energy level, indicated by n equals 2, now there are 2 sublevels. They are called the 2s and the 2p sublevel. Each grouping of horizontal lines corresponds to a distinct sublevel within that principal energy level. As we can see, there is 1 orbital in the 2s sublevel, 3 orbitals in the 2p sublevel. When we go to the third principal energy level, now we have 3 sublevels called 3s, 3p, and 3d. Are you detecting a pattern here? The 3s sublevel has a single orbital, the 3p sublevel has 3 separate orbitals, the 3d sublevel has 5 separate orbitals. When I go to the fourth principal energy level, now continuing the pattern, we have 4 sublevels called the 4s, 4p, 4d, and 4f sublevels. The 4s sublevel, like any s sublevel, consists of a single atomic orbital. The 4p sublevel, like any p sublevel, consists of 3 separate atomic orbitals. The 4d sublevel, like any d sublevel, consists of 5 separate orbitals. The 4f sublevel consists of 7. As you will see, there are patterns here. There are n sublevels in the nth principal energy level, meaning the first principal energy level has 1 sublevel, the second has 2, the third has 3, the fourth has 4. If you count the total number of orbitals in a principal energy level, you'll see an interesting pattern. In n equals 1, there's 1 orbital. In n equals 2, there are 4 orbitals. In n equals 3, there are 9 orbitals. In n equals 4, there are 16 orbitals. 1, 4, 9, 16. What's the pattern? Perfect squares. So we see our second pattern. There are n squared orbitals in the nth principal energy level. Now, the question is, what do these orbitals actually look like? Remember, an orbital is a region of space around the nucleus where the electron is likely to be found. From the wave functions, we can derive what are called probability distribution diagrams that show the 90% probability limits for each orbital, meaning the volume around the nucleus where there is a 90% chance of finding the electron. Remember, don't think of the electron as a particle, think of it as a wave, but we can still talk about regions of space where there is a high probability of finding the electron. S orbitals are always spherical. P orbitals, remember there are 3 p orbitals in any p sublevel. They're called the p sub x, p sub y, and p sub z. Each p orbital is a separate orbital, and it consists of 2 lobes of electron density that are pointed along one of the 3 Cartesian coordinate axes. This is the p sub x on the x-axis, this is the p sub y on the y-axis, and this is the p sub z on the z-axis. For example, here are depictions of the 2s orbital, which consists of a single spherically symmetrical orbital. This diagram shows the 3 2p orbitals, that is the 3 separate atomic orbitals in the 2p sublevel, the 2px, the 2py, and the 2pz, superimposed on one another. And remember, at the origin of the 3-dimensional Cartesian coordinate system is the nucleus. Okay? And I will share with you a link that lets you look at more complex orbitals. We can't see it from here. Now, the final part of the quantum mechanical model of the atom has to do with a property of the electron called electron spin. All subatomic particles have this property called spin, and it is a property that describes how the particle is oriented in a magnetic field. Different subatomic particles have different values of spin. For an electron, there are 2 possible values, +1/2 or -1/2. Essentially, you can think of it as spin up or spin down. It isn't really the same as the electron spinning on its axis like a top, but if it helps you to think of it that way, you can. Now, the significance here comes in the Pauli exclusion principle. The Pauli exclusion principle says that no two electrons in the same orbital can have the same spin. If one of the electrons has a spin of plus 1/2, the other must have a spin of minus 1/2. Well, the importance of this is the fact that there are only two values of electron spin. That means that an orbital, a single atomic orbital in an atom, can hold up to 2 electrons as long as they have opposite spin. Okay? So now we can add a further part to the quantum mechanical model of the atom, which basically says each orbital in a sublevel can hold up to 2 electrons as long as they have opposite spin. So here's what this means for the hydrogen atom. We'll go back to our energy level diagram for the hydrogen atom. Again, these are the first 4 principal energy levels divided into sublevels, and each sublevel contains varying numbers of orbitals. Oh, look, here's an electron. This arrow represents an electron, and it can either be pointing up or down to indicate spin plus 1/2 or spin minus 1/2. This diagram represents the hydrogen atom being in its ground state because the electron is in the 1s orbital, the lowest energy orbital. If I excite the hydrogen atom by adding energy, I can excite it to any one of these higher energy quantized principal energy levels. Here's the first excited state, here's the second excited state, here's the third excited state. Now, however, because we see there are multiple orbitals in each principal energy level, if I excite the hydrogen atom and promote the electron, say, from n equals 1 to n equals 3 in the second excited state, there is an equal probability of the electron being in any one of these 9 orbitals. So each of these diagrams represents a different excited state of the hydrogen atom. Okay? We'll go back down to the ground state. Now, coming up next will be how we use these principles to describe every other atom on the periodic table past hydrogen, namely polyelectronic atoms. And that will be the topic of our next video.